हेलो एवरीवन। सो वेलकम बैक टू माय चैनल। आज हम स्टार्ट करने वाले हैं मैग्नेटिक इफेक्ट ऑफ इलेक्ट्रिक करंट चैप्टर। आई थिंक माय स्क्रीन इज रेडी। तो चलिए आज स्टार्ट करते हैं हम अपना न्यू चैप्टर दैट इज मैग्नेटिक इफेक्ट। बहुत ही डेप्थ में स्टडी करेंगे। दिस वीडियो इज हेल्पफुल फॉर दोज स्टूडेंट हु आर इन क्लास 10th and 12th and who want to study this chapter in very depth from the beginning. Chapter is magnetic effect of electric current. Magnetic effect of इलेक्ट्रिक करंट का जो मैग्नेटिक इफेक्ट है उसके बारे में हमें स्टडी करना है। ठीक है क्या? देखिए पहले हम ये बेसिकली हमारा मैग्नेट वाला चैप्टर है, मैग्नेटिज्म चैप्टर है, जो कि हमारे क्लास 10th में भी आता है। सीबीएसई बोर्ड हो या आईसीएसई बोर्ड हो या फिर क्लास 10th में बेसिक स्टार्टिंग लेवल पर चीज़ें ये काम आएंगी। सो फर्स्ट ऑफ ऑल वी विल स्टडी अबाउट what is how we will define magnetism. First of all we need to define at least magnetism होता क्या, what is magnetism. मैग्नेटिज्म को हम डिफाइन करते हैं कि जो स्टडी ऑफ द प्रॉपर्टी ऑफ द मैग्नेट, जो मैग्नेट की प्रॉपर्टी को स्टडी करता है, दैट इज कॉल्ड मैग्नेटिज्म। दैट इज द स्टडी ऑफ properties of the magnet. The study of properties of the magnet is called nothing but magnetism. यानी जब मैग्नेटिज्म इज नथिंग बट प्रॉपर्टी ऑफ द मैग्नेट, जब हम मैग्नेट की प्रॉपर्टी हैं दैट इज मैग्नेटिज्म। ठीक है, नेक्स्ट विल कम हाउ वी विल डिफाइन मैग्नेट। हाउ वी विल डिफाइन मैग्नेट। ठीक है क्या? मैग्नेट को हम कैसे डिफाइन करते हैं वो देखते हैं। स्लोली स्टार्ट करेंगे, स्टार्टिंग से यहाँ से, और फिर धीरे धीरे हम लेवल अपना पहले बेसिक चीजें पढ़ लेते हैं कि हाउ वी विल डिफाइन मैग्नेट। मैग्नेट इज बट अ सब्सटेंस, इट इज अ सब्सटेंस which will attract small pieces of iron, nickel and cobalt. Okay, it will attract substance like iron, nickel और cobalt. ठीक है, और क्या हुआ मैग्नेट की what else is the property of magnet? पहले तो ये आयरन, निकल, कोबाल्ट के स्मॉल पार्टिकल्स को अट्रैक्ट करेगा, साथ में खुद को अलाइन कर लेगा ज्योग्राफिकल नॉर्थ एंड साउथ डायरेक्शन में जब सस्पेंडेड फ्रीली। जब किसी मैग्नेट को हम किसी टॉप सरफेस से, ऊपर के सरफेस से सस्पेंडेड कर लेंगे, व्हेन इट इज सस्पेंडेड फ्रीली फ्रॉम अ वॉल, ठीक है क्या? लेट्स से दिस इज द वॉल एंड हमने एक थ्रेड के थ्रू सस्पेंड किया। यहाँ पर मैग्नेट का एक नॉर्थ पोल है, साउथ पोल है, तो ये खुद को ज्योग्राफिकल नॉर्थ और साउथ डायरेक्शन में अलाइन कर लेता है। ठीक है क्या? इट विल अलाइन इटसेल्फ इन द फॉर्म ऑफ ज्योग्राफिकल नॉर्थ एंड साउथ डायरेक्शन। ओके, नेक्स्ट फॉर सब्सटेंस टू बी अ मैग्नेट, अगर किसी सब्सटेंस को मैग्नेट कहना है तो उसके पास क्या प्रॉपर्टी होनी चाहिए? फॉर अ सब्सटेंस to be a magnet, if there is substance it's a magnet, so what should be its property? So that we will call this as a magnet. So any idea like what can be the property, what will be the property of substance that we will call it as a magnet? So the property will be that it will attract small pieces of iron. First of all, property, it will attract small pieces of iron. Small pieces of iron को this will attract. Second, it will come to rest. It should always align itself in the north-south direction when it will be suspended freely from the wall. Okay, it will align itself it will align itself in the geographical north and south direction, or it will come to rest, or it will come to rest in north and south direction. It will come to rest in north and south direction, geographical north and south direction, when the magnet will be, or when the substance will be freely suspended. So this is the property of the substance to be a magnet. Now next, moving forward, we'll see what are the types of magnet. What are the types of magnet? Okay, what are the types of magnet? Now talking about the types of magnet, we can say that we have two types of magnet. We have two types of magnet. Okay, the first one is natural magnet, and the second one is artificial magnet. First one is natural magnet, and the second one is artificial magnet. Artificial magnet, or we can also call this as man-made magnet. Man-made magnet. Okay, so first of all, we will see what are the some of the examples for the natural magnet. For some of the example of natural magnets are Fe3O4 magnetite, Fe3O4 magnetite, black iron oxide. These all are nothing but natural magnet. Black iron oxide and lodestone. These are some of the examples for the natural magnet. What are the examples? Fe3O4 magnetite, black iron oxide and lodestone. Talking about the artificial magnet or the man-made magnet, we'll see some examples for artificial and man-made magnet, and the example will be like bar magnet. Second, horseshoe magnet. Horseshoe magnet. Third, ball-ended magnet. Ball-ended magnet. So these are some of the like basic examples of natural magnet and artificial magnet. So note these examples very clearly in your notebook. And now we'll move further to define what are the classification of material, like how we will classify some material. If we have some different kind of materials, so how we will classify material? We can classify material as magnetic material and non-magnetic material. So here now we'll see the classification of material. For a better clarity, or for if you feel like the video speed is slow, you can watch this on 2x speed or 1.5x speed. Classification of material, like we can classify material in the two types. First of all, magnetic material. And the second is non-magnetic material. Magnetic material means those materials which are attracted by a magnets are called magnetic materials. Some of the examples we can see here is like iron, cobalt, nickel, and their alloys. Iron, nickel, cobalt, and their alloys. These are some of the basic examples. Of magnetic material. Now, talking about the non-magnetic material, like such materials which are not at all attracted by a magnet, like something very common like wood, bottle, glass. These materials, if we have bottle of what? Fiber, plastic. Okay, plastic. So these materials are not attracted by a magnet. Okay. Moving forward, we'll see what are the properties of magnet. What are the properties? We'll deal with the properties of magnet. So put the next heading, properties of magnet. So if we have a material which has a magnet property, like which is a material or which is a substance which attract a small pieces of iron, and when it is suspended freely, then it aligns itself in the north and south direction, then that is nothing but that is magnetic material. It is magnetic material. Okay. One of the property, this property was all given by the William Gilbert. He is from England and he is one of the scientists. And he mentioned about the properties of the magnet. The first property of the magnet he explained is attractive nature. First was attractive nature. Means if there is a magnet, then it will be having attractive nature. Means it will attract a small pieces of iron. It will attract small pieces of iron, nickel, cobalt. Okay. Let us consider. Let us consider we have a bar magnet. So obviously it will be in what shape? It will be in the shape of cuboid or in the shape of matchbox, something like this. Take okay. So and here we have south pole and here we have north pole, and this is something middle region which is nothing but neutral region. This is nothing but it's a neutral region, and one part at the end is south pole. S is nothing but south pole and N is nothing but north pole. N is nothing but north pole. So if we have a bar magnet, if we have a bar magnet, let's say this is the 2D view, two-dimensional view, and you have north pole and south pole, and there are some iron filling particles. So iron filling particles will get so much attraction near the pole. So most of the iron filling particles will be attracted in the pole side, and here also most of the particles will be attracted in the pole side, and very less attraction will be there. Very less attraction will be there at the center. Very less attraction means because the magnetic field strength is very less at the center of the magnet. Okay. So if we draw the magnetic field lines, or if we see the arrangement of a iron filling particles around a magnet or around a bar magnet, it will be like this something. This is north, this is south pole, and this is center point, center region, and the arrangement of the iron filling particle will be something like this. Okay, it will be something like this. So iron filling particles will arrange itself in this manner. These small green particles, we have assumed that these are the iron filling particles, and they are arranging itself in this manner. Okay. So they are arranging. So this is the pattern how their iron filling particles are attracting and making or a pattern. Here, the reason there will be no iron filling particle. No iron filling particle will be present. No iron filling particle will be present. Why? Why it is so? Because why it is like this? Because the attraction is very less here, and in this north pole and the south pole, maximum iron filling we can see. Maximum iron filling particles we can see, because here is the maximum attraction. At the pole the attraction is maximum attraction is present here. Okay, we can also do the same experiment. Here we have done for the bar magnet. We can also do for the horseshoe magnet. We can also do for horseshoe magnet, same thing will be there. Horseshoe magnet. Here will be a horseshoe magnet is look like, how it will look like? It is a U-shaped magnet, right? If we draw the 2D diagram, if we draw the 2D diagram, it will look like something this. Okay, it is a U-shaped magnet, and here will be the north pole and here will be the south pole. So maximum attraction will be where? Maximum attraction will be in the north pole and south pole region, and in the center region attraction will be very, very less. So maximum attraction and iron filling particles will be here. Is it clear? Okay. Now moving to the next, that is pole of a magnet. Now we will second discuss. First of all, we have discussed about the attractive nature. Second is pole of magnet. Attractive. First of all, we have discussed attractive nature. Now poles of a magnet. If look at here, if you have a bar magnet, and this is north pole and this is south pole, then the distance between the north pole and the south pole will be actually not exactly this much. It will be little less. It will be something less, something like this. Okay, it means what? If we have a length L, if the bar magnet corner to corner length is L, so the distance between north pole to south pole will not be L, it will be slightly lesser than L, and it will be 0.84 L. Okay, it will be 0. Let us consider if the L value is 100. If L value is 100, then the distance between the poles, then the distance between the pole will be just 84. It means it is 16 less, minus 16. Okay, so this is actually how it exists. If L is the length of the magnet, then the distance between the pole, I'll mention here what are the things required here. If L is the length of the magnet, L is the length of magnet, then distance between the pole, then the distance between the two pole will be just 0.84 L. Distance between two pole is 0.84 L. Is it clear? Is it clear? So now we'll move to the third property, that is directional property. We'll move to the third property, that is directional property. Directional property. So what is the meaning of directional property here? Directional property means same thing. Already we have discussed that when a magnet is suspended freely, then it will align itself in the north and south direction. Okay, that only. Same thing. Align itself in the geographical, align itself in geographical and north and south direction. Geographical north and south direction. Geographical north and south direction. That's it. So this is the property. Now, what is the next property? Next property is like pole attract each other and unlike pole repel each other. So like poles repel each other, like pole repel each other, and unlike pole attract each other. Repel each other and unlike pole. Unlike pole means north and south. Like means north with north and south with south. Unlike pole attract each other. Okay, so this is the property. Next, fifth property we'll discuss about the magnet is magnetic pole always exist in pair. The magnetic poles, it will always exist in pair. Exist in pair. Magnetic pole, it always exists in pair. It means what? If we have a north pole, then obviously there will be a presence of south pole. It will be never like this. It will be never like a situation will arise that a small magnet or a very small magnet will have only a north pole. Okay, so it always exists in pair. If you have a bar magnet, let us consider we have a bar magnet, and at one terminal it is north pole and one terminal it is south pole. So if we cut this bar magnet, in small pieces, so this small all pieces will have north and south direction, north and south pole. This all magnet will have north and south pole. Okay. That means if you break the magnet in various pieces, in number of pieces, then also no issue. There will be a presence of north and south pole for the each part. Is it clear? Okay. Now, next property will be our inductive nature. Inductive nature in the sense, next property, sixth one, next property will be inductive nature. What is the meaning of inductive nature here? What is the meaning of inductive nature? Inductive nature in the sense, if you have a magnet like little knots, obviously this inductive nature is very like appreciable in the case of heavy magnet, but just we are discussing about the normal magnet, not that much heavy also, but normal magnet. So if you have a normal magnet and let's say we have a bar magnet, okay, and this bar magnet is totally covered with the iron filling particles because it is attracting, they are attracting iron filling particles, so it is totally covered with the iron filling particles. So look at here, if one iron is attracted very closely or directly attached with a magnet, you can see here, if this iron filling particle is directly attached with the magnet, but these iron filling particles, these far one which are present little far, these are not directly in contact with the magnet, these particles are not directly in contact with the, and these are in indirect nature, they are indirectly contact. So that's why like since they are not directly in contact, they are indirectly in contact, so they are getting the induced magnetism property. The this particle, like the who is directly in contact is this one, who is directly in contact, this particle are behaving like a magnet, these particles are behaving like a, start behaving like a small magnet, and it will attract a small pieces of iron on its upper surface, on its upper surface, and you can see here these are the magnet particles attracting on the upper surface. Okay, it is like this something. Okay, so these are the things which are present. Okay, now coming to the how we will plot the magnetic field lines of magnet. Now next we will discuss how we will plot, or first of all let us see how we will define magnetic field lines. How we will define magnetic field lines. In order to define magnetic field lines, we can say like it is nothing but an imaginary line. It's nothing but an imaginary line. It is, these lines are such that if we draw the tangent at any point, it will give the direction of magnetic field at that point in the space. Okay. So look at here. We can define magnetic field line. We'll write it short. MFL is an imaginary line. Is an imaginary line. It is nothing but an imaginary line, and these lines are such that the tangent drawn at any point, the tangent drawn at any point, drawn at any point in a region, the tangent drawn at any point will give the direction of magnetic field at that point, will give the direction of, will give the direction of magnetic field lines at the point, will give the direction of magnetic field lines MFL at that point. Is it clear? Is it clear? So again we'll move further and we'll see how we will plot magnetic field lines. How we can see of magnetic field lines. So plotting magnetic field lines of magnet. Magnetic field lines of magnet. So how we'll plot the magnetic field lines of magnet? We can plot magnetic field lines of magnet by with the help of a bar magnet. Like with the help of bar magnet in the sense, keep a cardboard, a big cardboard, and we'll keep that cardboard on top of a bar magnet. On the top of a bar magnet, we'll keep this cardboard, and if we spread the iron filling particles, or if or instead of that, we can use compass. We can use the compass, and we'll see when we are moving the compass according to the direction of the needle. We can see the compass, we are moving this compass one by one moving forward, and we saw that the magnetic field lines are pointing the arrow in such a direction, in this direction, like this, then like this, then like this. These were the direction of arrow in the compass when we were moving the compass one by one in the further forward direction. Then we can see the direction of needle, and like this we have plotted the magnetic field lines which is existing in a particular region surrounded by the magnet. So by this it is clearly that magnetic field lines are forming a circular loop. So we can see that these are nothing but these are forming a circular loop. So one by one, when we start drawing all these magnetic field lines, we saw like this. So these were the pattern of magnetic field lines. It means what? Magnetic field lines were forming a closed circular loop, and as we are going little far from the magnetic field lines curvature was increasing greater and greater. So here we will assume that these are the magnetic field lines which are coming from very far, and these are the magnetic field lines which are going very far. So we are drawing just some lines only, and we are like neglecting. But will it be like this? Present in the entire region. Okay? It will present, and we can see the magnetic field lines are very dark. So many magnetic field lines are existing here. Magnetic field lines are existing here. In this region, magnetic field lines density is very high. So we will conclude that in this region, the magnetic field strength is very high. In this region, where magnetic field where magnetic this region where MFL magnetic field lines is very high, so we can conclude that we can conclude that the magnetic field strength is very high, or the magnetic field strength is very strong near the pole. And magnetic field strength is very strong, or strong near the poles of the magnet. The poles of magnet, and it is very less in comparison to this region. We can see the curvature, the distance between the lines are increasing as it is moving far and far. Okay, the distance between lines are increasing. Is it like this that in this region? Wait, I'll show. Will exist in all these regions. One more property is that magnetic field lines will not cross each other. This will exist in all these regions. So, okay. We can see one more thing, that magnetic field lines will start from the North Pole and it will go towards the South Pole. It will start from the North Pole, the outer region, in the exterior region. But what is the case in the interior region? What is the case in the interior? Like inside the magnetic field lines will exist or not? We will see. So for your question, the answer is yes, will exist inside the magnet, and the direction of magnetic field lines will be from South Pole to North Pole, from South Pole to in the interior region, and in the exterior region will be from North Pole to South Pole. I think I'm clear to everyone. Direction of magnetic field in the exterior region, what will be from North Pole to South Pole, and in the interior region of the direction of magnetic field will be from South Pole to North Pole. Okay. After drawing the magnetic of a bar magnet, now we'll see about the properties of the bar magnet. I hope I am clear with the above topic. Properties of the bar magnet. Properties of the bar magnet. Now we'll discuss properties of the magnetic field lines. Properties of the magnetic field lines. Look at here. First of all, we'll deal with the first property of the magnetic field lines, and the first property is they form closed continuous curve. They form magnetic field lines forms closed continuous curve. This is one of the property. Closed means the loop or the curve will be closed, okay, and continuous means one by one it will keep on going. It is not something like that it started here and it get the breaking here, stoppage here. No, it will be continuous, okay, and they will repel each other and are in the state of tension, and these magnetic field lines will repel each other. Magnetic field lines will repel each other. Second, we'll discuss externally the magnetic field lines move from north pole of a magnet to south pole. Externally, magnetic field lines moves from north to south direction or north pole to south pole. Okay, these are the things. Third one, inside the magnetic field lines direction will be from south pole to north pole. Already I said, right? Internally, the direction of magnetic field lines moves from south to north pole or south to north direction. Direction, it means they are talking about the pole. Which pole? The pole of the magnet. They are discussing about the pole of the magnet. And the fourth property we are going to discuss is fourth property, that the tangent drawn at any point on the curve will give the direction of magnetic field line at that point. Okay, already we have discussed all this. So first of all, just you need to write, if it is asked in a board exam or somewhere else, wherever you are writing the theory paper, the tangent drawn to the curve, at any point, the tangent drawn to the curve at any point on it means on which they are talking about the magnetic field lines. On it will give the direction of the magnetic field, will give the direction of magnetic field at that point. Am I clear? So what is the fourth property? That the tangent drawn at any point, if you draw the tangent drawn at any point will give the direction of magnetic field lines at that point. Okay. Now moving forward, we will see the fifth property. Now moving forward, let us see the fifth property is the magnetic field lines force do not intersect each other. Means the magnetic fields whatever are present in a particular region, they will not cross each other, because if they cross each other, then at the intersection point it will have the two. Let's say this is one magnetic field lines and this is one magnetic field. They will never cut each other like this. So magnetic field lines never intersect each other. They will never intersect each other, because if they intersect each other at any certain point, then it will give the direction of magnetic field. It will give two direction of magnetic field at that point. Let us say if here is the point. So if you draw the tangent, so this is the direction of tangent according to this magnetic field line. This is 2 magnetic field, this is magnetic field line 1. So according to according to magnetic field line 1, the tangent will be like this. So this is tangent 1 and this is tangent 2. So we can see that the same point has two directions, T1 and T2, which is not possible, which is never possible. Means anything in this entire world which is moving, it cannot move in two different directions at a certain point. Okay, any point which is moving, or any body or object it is moving, it will move in one particular direction only. They cannot move like together only in two different directions. Okay, so magnetic field line will never intersect each other. I think I'm clear with the fourth point. Fourth point was like, if magnetic field lines is something like this, so the tangent drawn at any point, let's say if we draw the tangent at point something P, the tangent drawn at any point will give the direction of magnetic field at that point. Clear? Coming to the sixth property. What is the sixth property? We will see the magnetic field intensity depend on the magnetic line of force. The magnetic field intensity, like how much is the magnetic field, what is the strength, it will totally depend the region where the magnetic line of field lines are more. If in a particular region magnetic field lines are more, it means there the force of attraction of the magnet, or the magnetic property, or the magnetism part will be very, very higher. So we can write it like this: magnetic field intensity depends on number of magnetic line of force. Lines of force. What is the meaning of magnetic lines of force? It is nothing but these part. Magnetic lines means these. We can see the magnetic lines. Magnetic line. So we can see the magnetic line of force are very higher in density here. So the magnetic field lines are very higher in density here. So magnetic field strength will be very high in this region, and but we can see the magnetic field lines are less here. We can see the magnetic field strength is less here. Okay, so magnetic property or the attraction property will be less in that entire region. Seventh property is in uniform magnetic field, the magnetic line of force will be parallel to each other. In a uniform magnetic field, the magnetic field lines which are magnetic field lines are parallel to each other. How? We will see first of all. One by one diagram. If this is the magnetic field lines, so the tangent at any point will give the direction of magnetic field lines at that point. Okay. Second, magnetic field lines will never cross each other. If they are crossing at each other, it means they are having two different tangent, and two different tangent means two different direction, T1 and T2. This was magnetic field lines 1. So this is B1 and this is B2. Okay. So this is never intersect each other. Never intersect each other. Okay. These will never intersect each other. Now, move forward. Just we talked about what about the uniform magnetic field. So in uniform magnetic lines of force, or the magnetic field lines will be parallel, something like this, parallel to each other. Okay. Initially showing magnetic field, and they are in uniform magnetic field, the magnetic field lines are parallel to each other. Okay. Next, now we'll make a note and note important point. Write some important point. First of all, the important point is Magnetic field intensity or the magnetic flux density is denoted with the letter B. Okay, so magnetic field density, magnetic field intensity, or magnetic flux density, or magnetic flux density is represented B. Second, SI magnetic field intensity, that is capital B, or SI unit of B is nothing but is Tesla. You have heard about the Tesla car, right? That Tesla only, capital T. Okay. Next, the third property, that only that in the uniform magnetic field strength will be higher, and in non-uniform, the magnetic field strength will be random. Third property we will discuss is will contain two things. First of all, magnitude, and the second is, let us take a situation. In this, the magnetic field lines are parallel. You can see, right? But and the direction is also same. What about these curves? In this also, direction is also same, and magnetic field strength is also. What about this? In lines are going little far. They are repelling, or they are something expanding. They are expanding in nature, and they are like something starting from these regions. So magnetic field strength will be in this region will be very very less in comparison to this. If you mark this region 1, and this magnetic field strength or the magnetic field intensity B1 greater than B2. Magnetic field strength in the region 1 will be region 2. Okay. Now we'll discuss the next part, that is magnetic effect of current. Magnetic effect of current. Okay. In magnetic effect of current, there was a scientist known as Ørsted. He has done one experiment for the, like, let's say here they are talking about current, right? It means there will be a wire, and in this wire, it is carrying some current. What Ørsted did, what his experiment was actually, what Ørsted experiment was like, he or a compass needle, he saw that a compass needle got when electric current was passed through a metallic wire which was placed nearby the compass. What he observed, that if there is a wire, if there is the representation of battery, already you have studied in the electric current, and here we are, the current is coming, and let's say if they are keeping some resistance and all, and if we arrange something like this, so once the current was started flowing, when the current start flowing, this is positive terminal, negative terminal, and this is the resistor R, and this is nothing but switch. Okay, and this is battery, something, write it like battery, EMF, or cell, whatever we can write, that is nothing but same thing. Okay, so if you point the direction or particular thing, like what is our geographical direction, something like this is north pole, this is south pole, this is north pole, this is north pole, south pole, and this is east, and this is nothing but west. Okay, east and west. So what Ørsted, if we are keeping a compass near the wire which is carried, okay, and let us see like horizontal and vertical line present in the compass. So what Ørsted did is, when he placed the compass needle or the compass near the, so if the current is flowing in this direction, let's look at here, it is coming like this, right? It means the current is moving from north to south direction, right? From north to south direction. So when the current was flowing from north to south direction, then the deflection was in the left hand direction or the west direction. Okay, that the direction of deflection of the needle, if the current flows from north to south, if the current is flowing, this was the direction of current, right? I is nothing but current. So here the current was flowing to south pole. So if the current is flowing from north pole to south pole, then the deflection of the needle, was the in the east. Okay. Once again, I will repeat the line. If the current flows south direction, then the north pole of the compass needle will move towards the east. So the deflection was in the east direction. Something like this. We draw a proper needle. So something. Okay. This is the center point of the needle. So it was moving towards east. The deflection. Everyone is clear with the conclusion that the wire is carrying the current from north to south direction, from north direction, then that deflect in the east direction. Okay. Next we'll take just the opposite part. Like if the current in the south to north direction, there's a wire, and that wire is carrying the current from south to north direction, from south pole to north pole, then the deflection of the needle of the compass will be in west direction. So needle will be something like this. Okay, so in the west, if this is and this is east and this is west, so we can see that it has been deflected in the west direction. Okay, the needle has been deflected in the west direction. Is it clear? Is it clear? If the current is flowing from south pole to north pole in the wire, like from south direction to the north direction, which direction, which south direction? It is nothing but it is geographical direction. It is geographical north and south direction. Then the needle will deflect in the west direction. Then where is the needle will deflect? The needle will deflect in the west direction. And if the current in the wire is moving from north to south direction, if the current is flowing from north to south direction, then the needle will deflect in the east direction. And when the current is flowing from south to north direction, then the needle west direction. I think I am clear with the conclusion of Ørsted experiment. Once again, I will repeat. If the current in the wire is moving from north to south direction, then the needle will deflect in the east direction. And second case, when the current is flowing from south to north direction in the wire, in that electric current wire, so the needle of the compass will deflect in the west direction. So now we'll move forward and we'll see snow rule. These are the rules. Now we are discussing the rules to find the direction of magnetic field. Rules to find the direction of magnetic field. In order to find the direction of magnetic fields, what we'll look on this. Okay. First of all, snow rule. What is snow rule? According to this rule, if current flow in the conductor from south to north, the conductor is kept over the needle, then the north pole of the needle will deflect in the west direction. I'll come again. I will repeat again. If there is a wire, or if there is a conductor, let us consider there is a conductor or a wire. Conductor in the sense we are talking about wire only. Okay. If we have this wire, okay, and the current in this wire are flowing from south to north direction, and we have a compass here. We have kept a compass here, and this compass a needle is there. So when the current in the wire is, or in the conductor is flowing from south to north pole direction, then the needle of the compass will deflect towards west direction. This is same conclusion what Orsted has did. There is nothing like something very strange. If this is north and this is south and this is east and this is west, then the compass needle has been deflected in the west direction. The same thing which Orsted did, Snow rule just gave in the form of statement. Okay, Snow rule was same only. Next, coming to the Ampere swimming rule. These are what? These are the direction of magnetic field. Okay. Second one is Ampere's swimming rule. Ampere's swimming rule. In this Ampere swimming rule, what we will assume that if there is a person, let us consider there is a person, okay, and he's sleeping on the big compass needle. Something is not possible, but practically. But let us consider that this is a compass lying on that compass needle. From his leg to the head. From leg towards head. This is the direction of electric current. Then the compass needle will deflect towards the left hand. This is the left hand, and this is the right hand, right? Then this compass needle will deflect in the left hand direction. Deflect in hand direction. What is this situation? Let me explain again. There is a compass needle. There is a big compass needle, and a person is lying on it. Assume there is a compass needle, and a person is lying on it, and the current is flowing from his leg part to the head, towards head. The current is flowing from the direction of leg to the head, towards head. Then the compass needle on which he is lying, that compass needle will deflect in the left hand direction. This is nothing but Orsted experiment only. All these things, Ampere swimming rule and Snow rules, they came. This conclusion has been made from the the conclusion has been made from the Orsted experiment only. Okay. Now we will come to the topic of magnetic field lines, or the magnetic field due to straight current carrying wire. Like what are the, in this also we will discuss some rules. So the next topic is magnetic field due to a straight current carrying wire. What is this? Magnetic field due to a straight current carrying wire. Straight current carrying wire. It's totally clear with the heading only that we are going to see about the magnetic field lines pattern, okay, in the case of straight current carrying conductor or the straight current carrying wire. So look at here. This is the wire, we'll assume it. This is the wire, and it is something like this, connected with a battery. Okay, something like this, and we have connected a ammeter. What is the main function, or what is the working, what the ammeter do? Ammeter is nothing but it's an electrical instrument which measures the value of electric current. Okay, I hope I'm clear with my words. So, and this is rheostat. We have connected a rheostat. Rheostat is what? This is nothing but a variable resistor. or a variable resistance whose value can be changed, okay, according to the demand or according to the requirement. We can change its value, rheostat. And this is battery positive terminal and this is negative terminal, and we have a key, and we have connected this like something like this, okay. And in middle of this, we have connected a cardboard, and we have passed this wire through a hole from top to bottom. From top to bottom, we have passed this from through a hole. So we can see the current will start moving from positive terminal of the battery, and it will go from positive to towards negative terminal. Okay, the current will come like this only. I hope I'm clear. Okay. So we can see that the current is moving from positive to negative terminal, as we have already studied in the electricity chapter. So we know that if there is a wire and it is carrying some current, so around surrounding that wire at every instant there will be existence of magnetic field lines, and that magnetic field lines, how it will look like, we are going to see that. Okay, how this will look like, we are going to see with the help of experiment. So what we'll do, in this cardboard we'll spread some iron filling particles. In this cardboard, let us we'll spread this iron filling particle. So what pattern we saw, that when we throw the iron filling particles on this, so the pattern of the magnetic field lines were in the circle. So what the pattern was forming was in the form of circle. So circular magnetic field lines pattern were formed in this case. So what was the conclusion? The conclusion was, if there is a wire and it is carrying some current, then magnetic field lines are surrounded by that complete wire is surrounded by the magnetic field lines, and that magnetic field lines form complete circular loop. Okay. What else things we can discuss here is, like, see, if we take a point 1 here and if we take a point 2 here, I will highlight the points here, point 1 and point 2. So my question is, at which point the magnetic field strength will be very, very high, and at which point magnetic field strength will be less? In conclusion, like, at which point we will have the high. So it's a simple, which is closer to the wire. Which point? The point on the magnetic field lines, which is closer to the magnetic field, sorry, which is closer to the wire, closer to wire, will have higher magnetic field intensity, will have higher magnetic field intensity. What are the things? I will mention the things here. This was a ammeter, and this was nothing but a cardboard, and on this cardboard what we have spreaded, these are iron filling particles. So this were the like, what are the things we have observed in this experiment. This is the circular loop which was made by the magnetic field lines. Circular loop of magnetic field lines. Circular loop of magnetic lines. Okay. Now we already saw what is the pattern of the magnetic field forming surrounding the wire. Around the wire, what are the magnetic field lines are forming, that we have saw. Now we'll move forward and we'll see the Maxwell Cork screw. Two rules we will see in this. First is Maxwell screw rule and right hand thumb rule. So one by one we'll go through. First one is Maxwell. Maxwell was a scientist who has also done experiments in many fields, especially in electromagnetism. Okay, so Cork. According to Maxwell Cork screw rule, if we assume there is a screw, let us assume that there is a screw, Okay, don't mind my not that much good, but yeah, I'll try my best. So something like that. Oh, it's very bad. So let us assume that this is the screw. Okay, and if we tie first, either we'll tight the screw or we'll lose it. Okay, so if we tight the screw, what will be the movement? What will be the direction? Whether it will be clockwise or anti-clockwise. Before that, I will make you know that our like needle of the watch. That is not. I'm not talking about the digital watch. I'm talking about the analog watch. So the needle of the watch, it will all needles, whether it is hour needle, minute needle, or second needle, all will move in the clockwise direction. In this direction, this direction is known as like from here, something like that. So this direction is clockwise direction. It's for those people who don't know this direction. So just for their clarity, I'm explaining this. This is clockwise direction. And the direction just opposite to this is nothing but anti-clockwise direction. Direction just opposite to this will be what? Anti-clockwise direction. Okay. Now, moving forward, we'll see that if we tight the screw, so this arrow is indicating the direction of magnetic field. This arrow, this one, I'm highlighting this. This arrow is indicating the direction of magnetic field. This is nothing but direction of magnetic field. So will go up to right hand thumb rule, and I'll make in which I will explain the next left part of the magnetism chapter. Okay, that will be lecture second or the part 2 of this continuing video. Okay, otherwise this video will become little longer. So what we'll do is we'll keep the rest of the things in the next video. Okay, so just we'll complete the Maxwell corkscrew rule and right hand thumb rule. So according to the Maxwell corkscrew rule, if this direction, this what is this direction? This direction is nothing but clockwise direction. Okay, so this is clockwise direction. So if the direction of the magnetic field lines, or if let us consider this is a wire we have kept in this direction, and we are assuming, or we are like trying to find out what is the direction of magnetic field line, and the current is flowing from top to bottom. Wire, and I is nothing but a current. Current is denoted with the letter capital I or a small I, and the unit of current is ampere, denoted by capital A. Okay. So if in the wire the current is flowing from top to bottom of the screw, then the direction of the magnetic field will be nothing but clockwise direction. If the current in the to bottom is moving from top to bottom, then the direction of the magnetic field line will be in the clockwise direction. And what about the second part, or the just opposite part of this? Like same thing. If there's a wire and the current in the wire is moving in the bottom to top, okay, we can write it like from bottom of the screw to the top of the screw, the wire, the current is flowing in the wire. Current is flowing in the wire. Then the direction of the magnetic field will be in the anti-clockwise direction, and direction of the magnetic field will be in the anti-clockwise direction. I think I'm clear with this. Next will be similar, actually not at all similar, it is just exactly same for right hand thumb rule. Just we are using our right hand thumb instead of a screw, and the procedure to find out the direction of the magnetic field line is same. Right hand thumb rule. How we'll explain the right hand thumb rule? What is the right hand thumb rule? If this is thumb, if okay, I'm making very bad, no issue. And these are the fingers which we have folded. All 4 fingers we have folded. Okay. and we are holding a wire. We are holding a hand, and the current in the wire is moving from bottom to top, something like that, from bottom to top of the wire. So the direction of magnetic field will be in the direction in which we have curled our hand. This is our nail part, right? We can see the nail here. Okay, so sorry for this. Okay, so the direction of the, if the wire, if the current in the wire is flowing from bottom to top, then the direction in which we are curling our hand, that direction will give the direction of magnetic field lines. Okay, so if it is going from bottom to top, so the direction is nothing but anti-clockwise direction. We can see the arrow. The arrow is in anti-clockwise direction. This is in anti-clockwise direction. Just opposite part of this, just opposite part of right hand thumb rule will be same. We will do with the right hand only. Just we need to opposite the direction of current in the wire. If this is the wire and the current is flowing from top to bottom, this time it is moving from top to bottom, then the direction of the magnetic field lines will be shown by our four fingers, which is curling. Okay, and the direction will come in the clockwise direction. So the direction will be clockwise direction. So that's it for the session. For this session, I'll make the second part of this video in which we'll complete the rest of the things. So we have completed up to right hand thumb rule. Now after this, I will continue the further part like magnetic field, how it will be look like for the circular current carrying loop, and then we'll discuss clock rule. Then we'll discuss the solenoid, then electromagnet, solenoid working principle, electromagnet working principle, horseshoe magnet we'll discuss. Then we'll discuss what is the difference between bar magnet is also known as permanent magnet. Then we'll see the direction on which the current carrying conductor. Then flaming left hand rule we will discuss. So many things are there. Then if a charge is placed in a magnetic field, so what will be the things happening in that? Everything we will discuss in that. Okay, so that's it for the session. We'll meet in the next video in the second part of effect of electric current chapter. In that second video, rest other things. Okay, so thanks for the session. Do like, subscribe, and share to my channel for the next further updates of the video. And if you want some more video in any other, so you can write it in the comment box. I will make some video in that. Okay, so thank you. We'll meet in the next session.